Hello, everybody. Welcome to the Quantum Seminar of this week. We have Christine Silberhorn here from Paderborn University. And I am continuously running into problems with my lecture to prepare for this quantum seminar. So now I was just looking for my headphones and was running back and forth, which is annoying. So I'm not super prepared to introduce her. But I know a few things, and one is we are collaborating actually in the MilliQuant consortium, which is supposed to bring industrial quantum light sources into applications, and we are building a gyroscope, and Christine Silberhorn's group is doing things with light. That's something that I've understood, and we are doing things with light too. And also another good thing is, I hope, she has a Wikipedia article that I'm going to post here, and she has like a lot of things on it actually, including tons of awards and memberships. So she is a membership of the Leopoldina. This is maybe you can say later what that is precisely, but I think it's a very prestigious thing. She received the Gottfried Wilhelm Leibniz Prize in 2011. She received a prize for her dissertation in 2003 from Erlangen, and she was born in Nuremberg. In 2020, she was elected to the Academy of the Arts and Sciences in North Rhine-Westphalia. So I guess congratulations to this. And we are super happy to have you finally, after it didn't work out last semester. We have you here today, and we are thankful for that.
Well, thank you very much for the introduction, and thank you very much for actually the invitation. I would have loved to come to Mainz, but unfortunately this kind of doesn't work out. Well, thanks also for the intro. Well, the Wikipedia article, I should say, it's not from myself. I don't know who put that up. I hope it's most of the things are correct, but yes, let me say that. Well, it's my pleasure to introduce to you my research area. And it's right, we are doing things with light. I entitled this presentation as Nonlinear Integrated Quantum Optics with Pulsed Light. It's a title which is rather technical, I'm aware of it, but the important thing is that we're doing quantum stuff, we're doing it with integrated optics, and we also play with pulsed light sources. Now here you see one of the devices, which I will later talk about that, but just to give you an impression, this is experimental work based on theoretical concepts, and I hope that during the talk this become more clear what we are doing. But since it is a rather technical talk, and I was told that I should introduce you to the field, let me start with a motivation, which is more a general motivation. What is really the driving idea behind the research what we want to do? I like to say that we are working on quantum networks, and the networks already give you, everybody of you have some idea what a network is, and this is what you see here on the left. And for me, this is a model system. It's some structure where we have nodes, and then we link them by some links, and then you see already what's coming from that is a rather complex large-scale structure. Now, this large-scale structure can be all kinds of things. And of course, if I'm talking about networks and quantum networks, I think the one thing is the quantum internet. And this is another buzzword you have heard, I guess, or you might have heard. So we're trying at the moment to introduce quantum communication over network structures. And coming from photonics, that's an important topic for sure. But it is also a model system, as I said, and we can learn much more. We can have this as a model for brain or neural networks. We can have such a network structure to study transport phenomena, where you can think that different excitations are hopping from place to place. And the motivation, what we want to do is, by using quantum physics or quantum optics, we want to understand what is it really what makes the system quantum, and where's the difference between classical and quantum. So this is the fundamental point of view of looking into that. And this is actually not an easy question, and I hope by the end of the talk, it becomes clearer for you what I mean by that. At the same time, I'm a photonics person, and the second motivation is photonic systems are great. I do love them because they're extremely clean. What's more difficult, though, is to go multidimensional. What I mean multidimensional is really to have large systems. This complex system was one thing which I showed you already. And why would you want to do that? I'm coming from the field of quantum communication, quantum simulation, where one driving motivation is definitely to implement in the photonic system quantum computation and simulation. I will say a few more words in a minute. Quantum metrology, there it's probably more surprising. Why multidimensional? Well, if you want to measure things, it's quite frequently the case that you do not want to have only one parameter, or you have here, as you see, a continuous spectrum, and thus multidimensionality also plays a role. Last but not least, also for information coding, you're used to two-dimensional information coding bits, but high-dimensional information coding is also a very interesting topic, and in particular in the framework of quantum system, because there this high dimensionality can give you distinct advantages. Now, within the talk, I will not talk a lot about photonic quantum computation, though it is also something which we are very interested in, and I want to make at least a few comments on that. Photonic quantum computation actually has a long history, and I think around 2000 there was a milestone paper called the Milburn paper, and it's quite interesting. You can see that it is sufficient to have linear optical components and put them together in a network to get a full-fledged quantum computer in principle. And the non-linearity comes from the measurement, and this is called linear optical quantum computation. This was great. Now we are not living in the year 2001 anymore, but 2020. We still don't see it. The point is that the experimental overhead is huge for this original process. I think it's 1 to the 8 or 10 to the 8 or 10 to the 9 photons, and we managed to handle these days. Well, nowadays maybe 50, but this is already something. So this is something which is very ambitious. Nevertheless, it gives a goal. There is something which we call quantum walks and quantum simulations. We also did some contribution on that, which is less ambitious because it's not a full computer. And there's something which is even more, which nowadays is known under the name of boson sampling. It's again the question, what can we calculate? And this is quite interesting because in 2011, Scott Arison and Alex Akipov came up with a system which is rather simple. You say, I have just a matrix, which is a random matrix, but it's a special thing. And I just put n photons into the system and ask, where do they come out? Surprisingly, this is a problem if you get it for larger systems, which a classical computer can't calculate. And this is quite interesting. It's not clear if it's useful, but it definitely is in the class of systems where classical computer can't help. And in that sense, this is really for demonstrating that quantum computation can do something different. This is sufficient. This is actually, and last year in 2020, the quantum computation advantage was shown using photons. It's a milestone experiment. I don't know who of you is working in optics. It's absolutely crazy if you look at that. This is really a rather complicated experiment. But nevertheless, what they managed, they realized really to implement a system, a physical system, the photonics, which you can't calculate the outcome with classical computer. And this is where the quantum photonic advantage comes from. Let me say a few more words because we're quite happy what they really implemented. They actually didn't implement the boson assembly, which I showed you, where these individual photons were coming in, but they used different input states, which were squeezed states. Why is that? Well, we were also looking to that back in 2017 and asked ourselves, how can we scale up photonic systems? Well, scaling up photonic systems with single photon input states is very hard. And some of you might know why. Single photon states are unfortunately states which we cannot prepare very nicely. States which we can prepare much better are so-called squeeze states or Gaussian states. And you can look what kind of photon statistics do they obey and how does that system belong if you pass them through the same unitary which was originally proposed. It turns out equivalently for the original proposal where boson sampling is hard, also the counting statistics which you can get out there for this other state is equivalently hard, and we have the advantage that it has better scaling. And it's quite interesting to see this development, and this is also a development where we have been participating and we will participate, but the experimental overhead to implement such system is really large. With that, let me briefly introduce my own group. I think this was kind of the motivation, showing you already jumping right into the topic, and I hope that you also see why we're interested in that high dimensional systems. Now, I'm heading the group. I have built up the group Integrated Quantum Optics in Paderborn, and I want to show you how it's composed because it's a little bit of the philosophy, how I think we have to treat photonics these days. If you're talking about photonic systems and we want to really engineer them and build up systems, we need different we have technology. What I mean by that is that we are really producing our own samples in our clean rooms. Can you hear me?
Yeah, there was a bit of a, I don't know, maybe it was me or the Helmholtz Institute, but I think now it's good again. Sorry, but it seems to be good again. Sorry.
Okay, hopefully, please just stop me. So we have this technology. I think this is something in photonics which has not been done for quite a while. We were spoiled because there's a lot of technology available from classical photonics, but we have to do our own if we want to have tailored photonics. The second subgroup I call devices, and in my group, the technology Christoph Eigner is group leader. Now, devices, it's not sufficient to have structures which we manufacture in clean rooms, but we have to make real devices out of that. And it was mentioned in milliquant. This is what we try to do there. Take structures and then build the infrastructure and do the quantum characterization that we have handheld devices, which we then can use for practical quantum technology. And the person who is my group leader there is Harald Hermann. And last but not least, we want then to implement these complex systems, and we want to do fundamental science, but maybe also applied science. And we call the subgroup there, led by Benjamin Brecht, is quantum networks. There we really look on these larger systems. And the way we approach that is that we say we need all these people together, working together, because what I want to do in networks and what I can do will depend on the technology which I have there. And to have all these different people working together is a big advantage, which we're trying to build up in Paderborn at the moment. Now let's go back to the physics. So the overall theme is we want to scale photonic systems. We want to implement large photonic systems in order to do something, in order to study fundamental questions, but also in order to build up a quantum photonics technology. Now, the way you can have this scaling up can be done in different ways. One thing, which is always good, is to use integrated optics. This is great because this gives you a scaling. The second approach is, well, don't use space as a multiplexing structure, but use time. This gives you brings you to the point of time multiplex system. And last but not least, you can use time in different ways, because time can be also temporal spectral properties. And this is, if you have pulse flight, you can use also so-called temporal modes of pulse flight. Now, what I want to try to do in this presentation is I want to give you insights in these different fields and what we do there, and show how you can scale up systems and what you can do with that. And I will be rather from a high level, but I'm happy to answer more questions. And this is also what we're pursuing. We're trying to figure out different ways how we scale our systems. Let me start with integrated optics and be a little bit more specific. What we are doing in Paderborn is nonlinear integrated optics, but I will give an introduction to that anyhow. Now, when I came to Paderborn, there was a classical optics technology group there. And I was saying, well, I'm doing quantum optics. It's great. I'm doing something completely new because I'm doing integrated quantum optics. And then people stepped back and said, well, what you're doing on large scale is actually something which we know for a long time. And it's true. It's actually, we should give credit to the people who develop integrated optics. It's a great field. It's an established field. And that we can use these ideas is great. And I bring you here a review from 1969, and I show you how quickly we can make that extremely modern, because I think it's interesting to see that the ideas we have, how we should build integrated quantum optics or integrated photonics, are heavily based on the know-how we have, which is actually an advantage of these integrated photonics. I show you how I make this article a very modern review. I just add everywhere where there's integrated optics a quantum in between. And then sometimes I have laser beam circuitry. Well, put quantum beam circuitry in that. And then it reads already more modern. Sometimes, unfortunately, I have to replace laser by photon source. I don't go into detail, but people working on single photon states, and I highlighted it already in the beginning, to have these single photon states is not trivial, is not very trivial, but anyhow, this is still possible. And then let me read the last sentence, because I really love it, because it reads very modern. If realized, this new art would facilitate isolating quantum circuitry assembly from thermal, mechanical, and acoustic ambient changes through small overall size. There you see already what we want to achieve with integrated quantum optics. And then economy should ultimately result. So you see already in 1969, people were dreaming of that, but this is exactly what we try to do with integrated quantum optics or integrated photonics these days. We keep the ideas which had been there, but we try to transfer them to quantum optics. I think it's great because we build on this know-how, but also in integrated optics there's challenges, and we bring in these fields together here. So let's go to a more modern review from 2012, which is about a photonic quantum simulator based on integrated optics. So what is it? So if you want to build such a photonic quantum simulator or a photonic quantum computer, what do we need? Here, the idea of a hybrid network is introduced. And what you see here is that we have one integrated structure, which is called here source circuit. The circuitry is basically a linear optical networks and detectors, which is single photon detectors. And this is how a photonic quantum simulator should look like. And you can find that in this review article, which is just cited here. Now, what you immediately find is this circuit is linear optics, and the source side is nonlinear optics. Now, most of the work still up to now have been using this linear circuitry. And why? And what is the big advantage of using integrated optics for quantum experiments? Well, exactly what I had in the original review paper. You have many spatial modes available. They are well controllable. You get the interferometric stability of large optical systems. You can have compact devices. You get the miniaturization, easy operation, well, whatever you call easy, but it's comparatively easy. And one of the things which you want to have and maybe can have is high efficiency. But this is what a lot of people are working on these days. High efficiency means that there's no loss in the circuitry. And with that, just using this linear part, we saw really a tremendous development, starting, I think, in 2008 in Bristol with Jeremy O'Brien's group, and then other followed. This is just a few selections from European groups, Paolo Mataloni in Rome, they're doing quantum walks. This is one example from Oxford, but there are more. It has exploded this field. Still up to date, most of the work has been concentrating still on the linear one. Now, the nonlinear part of this circuitry basically means the source part, and we have been working on that for quite some time, and there are still progress which have to be made. What do I mean by nonlinear systems? Well, what I mean is basically that I use a different material platform, lithium niobate. Here is the vision we are following. So you have a chip, and on this chip you have different functionalities. You see these integrated components. The chip should have minimized decoherence. Like in all integrated optics things, we want to have a stable and a scalable system. That's great. It's a property of integrated devices. The property using lithium niobate, a Chi2 nonlinearity, gives you highly efficient photon pair generation. So this is good for photon sources, as you see there. And equally importantly, maybe even more importantly, is that you have fast photon routing. So you have fast electro-optic switches that you can reconfigure that on a very fast time scale. And I think people start to realize more and more that this is really essential also for this quantum computation. And this is why we also have to develop that. The overall goal is then to implement complex quantum circuits and have a good platform for that. Now, the toolbox for that such integrated circuits based on lithium niobate is then passive routing, which you have also in this linear system. You can have generation and storage, photon pair generation, up and down conversion if you want to have different frequencies to be combined. Quantum memories can also be included in such integrated structures. You have the big advantage that you can have active manipulations with electro-optic phase switches, polarization conversion or space switches. This property of lithium niobate to have fast modulation feasible is what's used in classical telecom all the time. And the last component is interfacing. You have to have very good fiber waveguide coupling or dielectric mirrors and the end facets. The interesting thing is that all of these components have, or most of them have been developed for classical optics application. This is a big advantage of quantum photonics, but we need a tailoring and redesign for these quantum applications. This is why we produce them in our own labs. Now, how does that look? We have implemented over the last 10 years quite a lot of different types of devices. And this is really bringing experiments which are on bulk optical tables down, and examples are plug and play single photon sources, where you really can now have at least something which you can hold in your hands and carry around for quantum technologies. Noon-state photon pair production is a specific type of entanglement generated source. Generation of polarization entanglement, if you're familiar with that, the so-called queer type source, which is used a lot in these experiments. Free photon state generation via cascaded systems are feasible. Optical squeezing, waveguide resonators. We have very narrowband sources. Waveguide resonators with integrated modulators. So there you now start combining different functionalities. Quantum interferometers we are studying. And because I don't have infinite time, I just want to show you one device which we implemented, which is at the heart of quantum optics and which we kind of implemented as a benchmark device. Is already a rather complex device and shows you how these functionalities can work on. What it is, it's a Hong-O'Mantl interference experiment on chip. So let me start. What is a Hong-O'Mantl interference experiment? Hong-O'Mantl interference experiment is a very basic experiment. Here you see 4 different cases, and it's a 2-photon interference at a 50-50 beam splitter. So I consider the case where 2 photons are impinging on a 50-50 beam splitter, and you can imagine that in principle these 4 outputs are possible for the 2 photons come out. Now what you find if you do the maths, and what you may have heard in the quantum optics lecture, is that the case that the 2 photons enter at different ports interfere destructively in the quantum interference, and thus we know that in Hong-O'Mantl interference, if 2 photons imping on a 50-50 beam splitter, that both of them always will end up at one output port only. This is a pure fundamental quantum property of light of 2 single photons impinging on a beam splitter. It's at the heart of linear optical quantum computation, and in general one can say of all these quantum networking applications, also of boson sampling. Now this experiment is called Hong-O'Mantl interference because these were the people who did it for the first time. And the way you prove that is that you take a 50-50 beam splitter, you have 2 input photons, and you introduce a time delay between these 2 photons, and then you monitor with coincidence counting the coincidence. And what you will find is that you get at 0 delay, where we have exactly the situation which you have above there, no interference, no coincidence counts, which is the Hong-O'Mantl interference, while in classical optics you can't explain that. This was the experiment we wanted to bring on a chip, and for that we implemented a so-called parametric downconversion source and a 2-photon interferometer on chip with a variable delay which we could control with electro-optics. Let me show how that to you how that works. So we come in with a pump photon, and due to the interaction of the light with the material, which is specifically designed, a pump photon decays spontaneously in 2 signal and idler photons. This is the quantum state where you have 2 single photons. Then the first element which it hits is a polarization converter where we switch the polarizations, and it will become clear afterwards why we do that from the beginning. Then in the next step, we have here what's called a PBS. It's a splitter of the 2 polarizations. We split it in 2 different spatial channels. And the next element we see here is another polarization converter. And these 2 photons are split because they have different polarizations. And the point is that lithium niobate is birefringence. So H and V photons travel at different velocities. So if you switch them correctly, and then they have the same polarization, here there's a 50-50 beam splitter, there's no time delay between those 2, and you see the interference. If you switch them at different delays, it's traveling for a longer time. It's an H-polarized photon, and thus a delay is introduced. And if I introduce a delay, I have the situation that I don't see that effect. We call it bunching, that they both exit at the same output port. So what we expect, depending which segment is switched, we should have for the right timing that there's no coincidence like in Hong-O'Mantl interference experiment. And if we switch it at the wrong timing, we introduce a delay. By the way, this is the reason why we switched from the beginning. If you wouldn't have switched from the beginning, there's always a delay because of the birefringence. This was theory, this is experiment, and what you can see from that is that the device works quite nicely. We can now replot the situation, not in these segments, but we calculate how much delay is they introduced. And what you receive is for the device. Here on the left, you see a photograph. That we get a beautiful Hongo-Mandel interference chip. This is nice, and the visibility is 93%. At the time delay which we can introduce for that is 12 picoseconds. This is an interesting experiment for us because it shows that all these different elements work together. The switch is an electro-optic switch, so it can be arbitrarily fast because this is demonstrating this advantage. And you can mention that this is a really benchmark device where you can introduce it for all kinds of different systems to really get time delays customized as you want to also. So this is, for these integrated devices, is the status where we are. And now we're developing more complicated things like interferometers for quantum sensors. With that, this is the intro to the integrated quantum optics. I would like to switch gears. And here you see now photograph looks completely different. And this is how we do it. We are not only developing the integrated optics devices, but we also want to do, in the meantime, before we have the complex structures for that, quantum optics experiment on optical table. And this is what we do in this time-multiplexed system. And it's a different way of getting to larger Hilbert spaces. And here you see, well, a lot of optical. This is, I don't know, standard optics lab, what you will typically find. So let me get introduced to you to the time-multiplexing. What do we with the time-multiplexed systems? This is in the direction of the spirit of quantum communication, quantum simulation, or quantum walks. And let me give you a brief introduction to random versus quantum walks. This is again very basic. A random walk is basically, we have this little guy, he's drunken and doesn't know where to go. He walks on one line, we say, just in one direction. And he throws a coin, and depending on the coin, he either takes a step to the left or to the right. Now, what you get from that is depending, well, and you get these step by step. And what this is a golden board. And what the distribution you end up with at the end is a binomial distribution. This you know from random walks, and I guess this is what we learn at school actually. And it's characterized by the fact that the variance of this distribution is proportional to the number of steps. Now, if you translate this to the quantum world, what we do is we introduce for that coin space now a two-dimensional Hilbert space. In our case, it's a polarization. Depending on the polarization, now we do go steps to the left and the right, but because we're in quantum mechanics, we now produce superposition states. And if you ask how this actually looks then in the quantum case, the coin is a quantum state. We are producing superpositions, and these superpositions we cause interferences. And if we now look at the output distribution, we get a completely different distribution. It's related to the ballistic propagation, and the variance scales with a number of the squared step size. And this is now one definition how we can distinguish between random and quantum walks in this scenario. Here you see what you want to do is you want to let the system operate over many, many step size. And here, if you do it over 100, you see a clear distinction between the classical binomial distribution of the particles via the quantum distribution, which has these interference properties. And this is exactly the question I raise here. What makes a quantum system quantum? And what makes it quantum in this case basically is simply the fact that that single particle has an interference phenomena. So quantum versus classical here means that we see all these different interferences. And it's definitely the wave-particle dualism I just described with you with many, many slits. Now, why is that interesting? Well, the random walk is used in classical computation for the simulation of all kinds of things. Classical processes like Brownian motion, biological systems. In information science, if you look what really the Google search algorithm is, it's based on a random walk. Going to superpositions, we see is one way how we get these random walk algorithms over to the quantum side. And it shows you that these random walks can be good models for studying propagation phenomena in semiconductor physics. Quantum biology might be one way where you can approach and try to simulate systems. And well, most importantly, this is also where it comes from quantum computation and simulation. Now, if you want to implement these in experiments, how can we do that? And here I give you the benchmark I typically would define. We want to have a system which is reconfigurable, because this reconfigurability ensures you that you can change parameters which we need for simulations. You need a stable system and a scalable system. And you can have different ways, but one way which we pursue for more than 10 years now is time multiplexing, because it's a very resource efficient way. How does that work? We implement a very specific type of interferometer. We first come here in with an input state, which is a pulse. And then here this EOM, ignore it for a moment, I will later on explain what it is. We come into the double loop structure. Here you have the coin state. Our system is implemented in polarization degrees of freedom. And at the heart, we have now a system where, depending on the polarization, we have polarizing beam split, and we either pass through a long fiber or short fiber. And this implements a step. And then we recombine and feedback the system in a loop. Let me explain in detail what it is. So we're coming in, we have the coin here, and this coin spread is polarization, where we can, with a half-wave plane, or well, choose any polarization. Now we are in this double loop structure, and you see here, depending on the polarization, we either introduce a delay or not. So we have a step operation, relative shifts in time correspond to steps in position space. Now here we have in the setup at this point, and we come to the feedback loop. And what it does is we send the same pulses back into the system. And now you see that there could be short, long, long, short in the system. And we get, for the one where they have traveled at different cycles, different paths, the interference. This is nice because this is now exactly doing what the quantum walk formalism tells you. And if you replace this half-wave player, if you add another electro-optic modulator, you have here a programmable system where we can program all kinds of different dynamics. And this is actually quite neat, but you can really use it as a simulator. In that one D-walk implementation, the other advantage we have is that we can implement rather straightforwardly a system which is rather large. So what you see here is rather old data by now, but it's a quantum walk over 28 steps. This is actually experimental data compared to theory paper, where we just used the system I just described. And if you want to implement these 28 steps in a spatial domain, you would need 406 beam splitter and 29 detectors. That would be a rather large system, but time is very efficient. And this is why we can implement with the time multiplexed system rather complicated systems. We have a very good resource efficiency. And moreover, because we're using the same elements over and over again, we have almost an ideal homogeneity, which is, if you have it in custom-made systems, not the case. And you see that we have a nice simulator platform here. Now, again, I don't want to explain you all kinds. I just explained to you the basic system which we have used for that. But we have implemented all kinds of things already. We studied decoherence and disorder, the losses, graph engineering, graph state engineering, percolation graphs. We can also look at two-dimensional systems. Then we looked at topological invariance, which is simulating semiconductor systems. We looked at higher dimensional coins, and you can also study measurement-induced dynamics. So this is because you have the system, this coherent evolution, which you can program all kinds of things, and more things are feasible. Now, I started with asking what makes a quantum system quantum. And I don't know, I'm sure that there's quantum optics people, and the criticism which we get all the time is, well, this is not a quantum system. And I kind of have to agree, because I said we have a single photon. Actually, we use recoherent laser light because it's the same thing, where mostly only single photons in that. And then there's a fully classical explanation, which is just with optics. So the way I see that is we can cross another boundary. If we really want to understand the quantum properties, which can't explain classically, we want to look at multi-particle effects. And this is what we did last year. So what you need to do is now we have to have, this is the circuitry, the network, the detection was already in there, but now we want to include a real quantum source, and we implemented one which is compatible for our source. If you're interested, I'm happy to tell you. for you, what's important to know, it's basically giving you the opportunity to have really two single photons be in the system. Now, what we wanted to understand is the coherent evolution we proved in our previous experiments, and that we can have this coherence nicely done was also clear. But we asked ourselves, what about these two photon interference, that homomundal interference, which is at the heart of quantum mechanics? How does that look in more complex systems? And for that, we set up the following experiments. We programmed our circuitry, the blue part, in such a way that we get different superpositions at the input here between the blue and the yellow part, and wanted to see what kind of detected two photon interference effects can we get. And the interesting thing is we programmed it such that in the one case, the two blue lines and the two red lines, the photons, are in exactly the same superpositions, and then they interfere delocalized on that beam splitter. And we measured them with these 4 individual detectors, or we measured them in a way that we took some of the counts together, and it corresponds to a time bucket detection, such we can analyze coherent features. Now, in the second phase, we did the same detection, but we programmed that blue network in a different way. Again, we had the same amplitudes, but we introduced a 180 phase degree between those two. And then we studied again this time resolved versus time bucket detection. And here you see the two cases once more. So the blue lines, either the blue and the red, are exactly the same, or we have different superpositions of these single photons which are delocalized there. Now it turns out if you do a measurement which you do resolved, so you ignore here the right-hand side completely and look what the homomundal interference does, or you ignore the left-hand side, so you look just on these individual detection events, and you find in both cases exactly the same. Why? We don't care that there's another part there, and then you see, yes, the quantum interference on these individual localized beam splitters works. The interesting part, so, is if you look at the time bucket detection, where you say, well, I don't care if it has ended up in the blue part here, left or right, on the red part, left or right. Then in the first case, where they're completely identical, you get again the same homomundal interference dip. While in the second part, you take these counts together, you get no interference whatsoever. Why is that important? Well, it turns out that in the global feature, we can kind of steer this quantum interference, the second order coherence interference, by playing around with the first order coherence. And I think this is very interesting because this phenomena, how these quantum properties belong and how this interference is really behaving, we can control by the classical properties. And it also highlights for me that the photons are the most important entities of these things. They can be distributed over many different modes. If you look at the end from the photons picture, we can get a very clear understanding which kind of interference pattern we can have. Okay, so far for the simulations, and now I ask you, how much time do I have left?
Well, definitely 7 minutes,
okay,
for sure. But I also promise you I will not interrupt.
So let's talk about the last topic, the temporal modes of pulse flight, because I saw that some people are also coming from a spectroscopy thing, and I think this is rather another way of scaling up these systems, but also understanding these photonic systems better. Let me first get you a brief introduction in these temporal modes and what their encodings are. We had already with these time bins, I kind of introduced already one time bin encoding. So we have different timestamps, and this timestamp we can just give different numbers, and this is one encoding. Can do the same thing in the frequencies. We don't care about timing. Here you don't care about frequency. Different frequencies have a different encoding. Now, these pulse temporal modes are something in between. If you look at frequency time space, they all are kind of on top of each other. So they live in the same area, so to speak, but they are pulsed systems because they have in time and frequency limited space, but they kind of have different envelope functions. I will explain in a minute what it is. And they are orthogonal modes. It's nice because they form a high-dimensional alphabet. And this high-dimensional alphabet you probably have heard in the context of spatial modes. Now, having them in the temporal domain gives the big advantage that they're compatible with waveguide devices and fiber networks. So this is a mode encoding which can be used in all kinds of different integrated network structures. The only problem we have is how we measure and manipulate them, because you can't just do a spectral measurement or a temporal measurement, because then you will mix them up again. Now, for the students, these temporal modes are not very simple concept, to be honest. Why? If you start introducing quantization, the first thing you do, and you might not even remember, is like, well, let's talk about monochromatic mode. This is single mode. And then we have one frequency, and this frequency is quantized. That's fine, except if you think about that, it can't be the truth in any experiment, because if we have one monochromatic frequency, you Fourier transform and you see it infinite time. So this is any experiment, it can't be, and it's a quantum bit rate of 0. You have to do something else. You have to introduce actually something which is we call temporal mode creation operator. It's basically you build up a wave packet with this. We give the single frequency a spread, the single photon a spread of frequencies as a coherent wave packet, and then we can nicely define time and frequency, because then we have something which is constrained in time and frequency. What we did, we introduced the envelope function, and here the most common envelope function you can introduce is a Gaussian. If you accept that, however, that we introduced for the single photons envelope functions, you can introduce all kinds of envelope functions. You can also introduce Hermite modes. And these Hermite modes, the envelope functions, then allows you to define pulsed temporal modes. So instead of dealing with individual frequencies, we now treat with different envelope functions. And they really have these orthogonal mode bases which we can play with. They overlap in time and frequency, but nevertheless, they consider nice Hilbert space. Now, if you look at this parametric downconversion process, you can basically engineer these things. You can either have the situation where we have specific properties of the waveguide and also the pump pulse, and then if you have a so-called decorrelated joint spectral amplitude, you really get from one pump pulse to Gaussian wave packets, and this is a scenario you want to do. And this is what's nowadays called spectral source engineering, and people exploit it a lot and do these things, and it's almost standard these days. But you can go one step further. You engineer it not only, but then you start and introduce shaping of the pump pulse. This changes this joint spectral amplitude, this structure, and this structure changes the number of these temporal modes you occupy. And this is quite nice, because this allows you now to really harness that for information encoding. The only thing you need is now you have to have a device which allows you, here's the input states now, which we just have generated in all these different temporal modes. You need a device which allows you to address specific modes. For example, here in the first case, only the Gaussian is converted here to a different frequency, and the rest is passed through. So this is like a WDM demultiplexer. We implemented, we proposed this concept in 2011, and nowadays we are introducing that. It's a specific some frequency generation process. And well, basically what we are doing here, you see it's called Schmidt mode decomposition. If you like, I'm happy to discuss all that, how it goes. But if you have this pictorial approach, which I showed you, basically we are now doing, we are implementing such systems with pulse shapers where we have these temporal modes, and we can design and decide exactly how we implement these different temporal modes. This is what this thing shows, and it always corresponds the structure between the frequency of sigma and idler translates into this dimension high dimension temporal modes basis. And then we implemented this pulse gate. It's the same thing I explained beforehand. So here we have the different temporal modes coming into our system. We choose with the pump pulse which one you want to convert, and we select these individual frequencies out. Here it's technical details how the quantum pulse gate is composed. For us, it's a home build. I think that's in lithium niobate waveguide with a very specific polling, because only then we have dispersion properties, and this is what's behind the scenes of this work, that we need these devices to implement that. But what we can do, we can select now arbitrary modes, and we can measure these things. And one thing we did, we implemented a 7-dimensional basis. 7-dimensional means that we do our information coding on these 7 different mode shapes. You see them here on the top, and they look a little bit different because we have intensity phases plotted. But if you're talking about bases, now we can come up with all kinds of different superpositions. And this is what in every of these single row, you see different superpositions. They all form a basis. This is important if you want to get for more complicated information bases in that. Then we did a tomography. Basically, we combined now a parametric downconversion with that mode structure, and we did the tomography of one of the output modes, and it works. This is the take-home message here. Here you see one example where we have this nonlinear waveguide pumped with the first emit mode. This gives us a temporal mode entangled state, so to speak, where 2 of these modes are present, and theory and experiment work together quite nicely. And what we find is that, yes, indeed, by having 2 nonlinear processes combined, which is a parametric downconversion process, which is tailored to our needs, and a sum frequency process, which is a quantum pulse gate, we can really operate on these modes. We are quite excited about that because we're bringing this now to applications. Basically, we can do quantum communication systems with that now. We can think of processing. We can think of all kinds of different systems. And nowadays, we're developing more along that line. And maybe in the last few minutes, we then figured out that you can do even more with that quantum pulse gate. And this goes back to one idea, which is parameter estimation of incoherent emitters. It comes actually from astronomy, where people were asking if I have in space 2 objects, 2 stars typically, which are incoherent emitters, and I want to estimate the distance between those 2. Well, depending how close they are together, we can either distinguish them or not. And what we do is intensity counting, and I think I don't have to convince you that there's a Rayleigh limit, a so-called Rayleigh curve. If you do that intensity measuring, here you have the separation, and the Kramer-Rao bound basically tells you what is the variance of these estimation, and if the separation goes to 0, then you just can't say what the separation is. Interestingly, if you do a quantum information theory, Zhang and others in 2016 have figured out if you do a different measurement, which is measuring on coherent modes, on superpositions, that this measurement doesn't exist. So mode selective measurements allows you to overcome the Rayleigh limit. Now, people have done that for the spatial modes, but I told you that with the temporal modes, it's the same analogy. And for us, it's this separation which we have is now not space, but time or frequency, can do both. And this is what we actually could show. So we program a system with 2 frequencies. Each of them of these light sources, so to speak, have some spread, and this is some width for that. And what we want to estimate, they're incoherent, we want to estimate how far are they apart. We could imagine spectroscopy, somewhere 2 things and we bring them closer and closer together. And what we find is that we can bring them much closer together. Here you see that, these 2 spreads, then the variance of that. And we can also overcome here this Rayleigh limit. And we find it quite intriguing. This is this mode selective measurements we can implement. And then this was still a rather artificial system because the height of these, here in this thing, the height of these had to be exactly the same. But the question is, if we now come to more realistic scenarios where we have unequal intensities and also a centroid is different, can we really measure all these parameters simultaneously? I don't want to go in the theory, but this multi-parameter estimation is hard. One way you can imagine is these different parameters fulfill themselves in the measurement basis, something like an Heisenberg uncertainty relationship. Not the state, but it's not clear that you can do it at all. But this year we managed to do so together with theoreticians. They told us on which mode we should project them. And here you see it's a separation, the centroid at different heights, and all these parameters can be estimated simultaneously. What you see in these graphs is that we change these parameters. The gray areas is what classical intensity measurement would give you. But if you do measurements which are not this intensive, but we use our quantum pulse gates, we can see that we can do much better on that. And I think that's quite exciting, where you see where also metrology, our methods can have applications. So the quantum, it was done with a quantum pulse gate measurement for adaptive gating pulses. With that, I'm slightly over time, I hope not too much. I would like to sum up. What I wanted to give you is an overview showing what is photonics capable of doing in more complex systems. I talked to you about nonlinear integrated optics, and there I basically introduced to you what is the concept of getting quantum photonics practical. I showed you the time-multiplexed quantum systems, which is in the area of quantum simulations, where I showed you the quantum walks and the coherent control, how you can control quantum interference phenomena. And last but not least, I took some time to introduce the concept of temporal modes and showed you how quantum pulse gate can be useful for information encoding in quantum metrology. With that, I would like to thank you for your attention, but I also would like to say that I'm very grateful to work together with a great team. It's not my work, it's the work of a lot of PhD and postdocs who are involved in these things. That's the whole group. And maybe to allow me, if you're interested in joining, we have a lot of open positions these days because we're building up quantum simulator experiments as well as quantum metrology, and we're very looking for people. Thank you very much for your attention.
Thanks a lot for the very interesting overview of your research field. Very interesting stuff, and also quite an impressive group. Hi. I'm actually just going over the names because I know someone. Yeah, no. Not so far. Well, are there questions? Maybe I start then. I was wondering, maybe you could repeat this. You're generating, like, I mean, first of all, it is the first time I hear that people are using those shaped pulses for quantum information. I find this very interesting and cool. But I didn't really understand why there is the superposition of a Hermite Gaussian and a Gaussian in the downconverted states. I didn't know where the Gaussian comes from. If you pump with a, maybe it's trivial.
No, it's not. This is a little bit. Let me try to jump to that slide. This is why I was a little bit quick, and I see that. Let me try to go to the intro and show it to you. Where it comes from is basically this slide. So if you pump a waveguide with a Gaussian pump and a nonlinear waveguide, what you end up with is that you get a joint spectral amplitude. The reason is simply, so this is the frequency of the signal and this is the frequency of the idler. And it's quite easy to see because of energy conservation and momentum conservation that you get a function f omega s, f omega I. I think that's acceptable, and this is a Gaussian function which has some alignment, and this alignment depends on the different velocities inside the waveguide. Okay. Now this function, however, you can write in a different way, and this is what this Schmidt decomposition does. Basically, what you try to do is you want to have individual. Well, it's a Schmidt decomposition, if you're but this is a matrix basically, which has all kinds of different entries. If you diagonalize this matrix, you end up with these different shapes where you can define this as this continuous function of these Gaussian Hermite functions. And it's a mathematical way of showing that, okay? And this is always where the structure comes from. Its structure comes from the correlation introduced by energy and momentum conservation. And then you can manipulate that, because if you have a pump field which is shaped, then this function gets changed.
Okay, so and if you now put a Hermite Gaussian into the pump field, then you have to really search for a specific, or look at a specific frequency to get this superposition of Gaussian and
yeah, if you have a meet function, I think I had in the intro. So if you have these different contributions here, energy conservation, this is momentum conservation. You can either yield, because this is as a decorrelated system, if I pump it now with this Hermite function, you see that you get a completely different structure, this F omega S omega I. And it turns out if you decompose that, it's a unique Schmidt decomposition which is associated with it. That you get exactly the system that you have one Gaussian and Hermite function, and a Gaussian, the mathematical analogy, so to speak. But it's unique.
And wow, okay, sorry, just sorry for being a bit slow there. I'm ill, so
no. This is the most. It's probably also a bad explanation because it's a mathematical thing you find. So this is.
What's the? I mean, the left picture is the pump pulse, and no, it's both. It's signal and idler. It's what comes out, but it sort of has the shape of the pump pulse, and then.
Yeah. Mm-hmm.
Yeah, sorry. And what's the middle picture where you show this Gaussian?
This thing. So
it's the output.
This is the output. So this is the input of the pump, and this is the output with signal and idler. This is the signal following the idler photon, and it's living in this different. It can have these different shapes. And if you ask, where does that come from? This is energy conservation. Now, this pump pulse is here. You have to. The pump pulse shape is aligned along 45 degrees because this is they have to add up. The phase matching, this is the velocities, how they go, and then you get this F omega S omega I. And if you ask, how can I write this in this form, you will find that's exactly one Hermite function combined with another Hermite function or the Gaussian. This is simply decomposing that in the Schmidt decomposition gives you the shape of signal and idler.
Thank you. Yeah, that makes it much clearer. Thanks. Are there other questions? You can just ask questions. We are people. Yes. Didn't understand something, ask a question. Okay, then maybe another thing. You talked about this. I get always very suspicious when I see it, like the super resolution, if you want fitting of a Gaussian. Maybe Rayleigh's curse, this is just the variance basically of the distribution you show there. And or is it too simplified if I say that what you do ultimately is sort of fitting it with the sort of point spread function, and then you get a bit better parameters, or is this too simplified?
This is too simplified. The point basically is, you're absolutely right to be skeptical. This is basically the technical slide. So this is the two Gaussians, right? These are incoherent functions. And if you just measure these Gaussians as intensities, which you do if you do fitting, if they're getting too close, they're getting too close, and you can fit whatever you want, but you will never get this resolution. So you have to do something different. And this is what's shown here. You're changing already the way you measure it. You don't measure these intensity distributions, but you instead project them on different functions. And the way you project them, let me see if you project them on the one hand on a Gaussian function and the other on the Hermite function. And this different projection, you're measuring fields instead of intensities. This does the trick. This is where this quantum Fisher information comes from, because you're changing the measurement per se. See, there's no intensity measurement in the system.
I see. So
I don't know if this is basically what we say, but it's not probably. Is this a projection on the field modes, which is important? And you could say from a classical point of view, you're measuring on these superpositions, which we do with this pulse gate too. And you typically, you can understand this is a coherent projection, but if you think of these Rayleigh curves, you never think of any coherences you're projecting onto, and this is the trick, so to speak.